To have this first seminar in our program. Sergei Fedotov from Manchester will speak about continuous random walk and nonlinear reaction transport equations. Thank you very much.
Right, thank you very much. Thank you for inviting me to give a talk here. It's a nice place, and I'm very grateful to organizers to give a talk here. Today I'm going to talk about the connection of continuous time random walk model and the microscopic nonlinear reaction transport equation. So I'm a physicist. I'm not going to prove theorems today. My purpose today is to look at microscopic reaction nonlinear partial differential equation from probability point of view. So that's my purpose. But first, let me give a brief outline of my talk today. At the beginning, it's introduction. I remind you about basic idea about reaction, convection, diffusion, PDE, scaling, how to take into account memory effects and long-range interaction, and then the connection with fractional partial differential equation and continuous time random walk model. And after this introduction, I'll start from my own result about how to implement non-linearity.
I just wanted to make a comment that in your talk is also a little bit of history.
Oh, right, yes. You mean introduction?
You know, the title is in French.
Oh, right, yes, I like French. That's it's not just because of history. And my own result about how to implement non-linear kinetic term into non-Markovian transport equation. So basically, I'd like to discuss the interaction of non-linearity and non-Markovian random process. And I'll derive nonlinear mass equation for mean field density and then apply this for KPP propagated Franz problem. And of course, it's the conclusion. Let me start with a very simple example. Let's introduce function rho, represent the density of particle at point x at time t. And so we assume we have a lot of particles, and we introduce the density, the number of particles per unit volume. And we assume that the number of particles tends to infinity such that we can introduce mean field. So we describe the process in terms of mean values. And this function obeys this equation. This is pretty standard partial differential equations, and you can see that the rate of change of density depends on convection term, where v is velocity, and this is molecular diffusivity, where d is diffusion coefficient. Well, this is a pretty standard stochastic partial differential equation. If we look at velocity field as a random field, and if it's, let's say, this velocity field describes turbulent flow, this is a very famous problem, how to find large-scale behavior corresponding to this stochastic PDE. But now the question is how to take into account reaction. The standard way to take into account reaction is we put nonlinear terms on the right-hand side. So I simply add nonlinearity. I would say, okay, this is nonlinearity described reaction, and this coefficient, which is function of time, density is reaction rate. For example, if I use for rho this function, 1 minus rho, this is famous KPP equation. A lot of work done on KPP equation. But for me, now the question is, why we add reaction term? Why it's additive? Why transfer term like diffusion separated from reaction? Do you know the answer? Why we separate usually? Of course, we can add on the right-hand side noise term, and we call it, this is stochastic PDE. Anyway, but we always separate convection, diffusion, and reaction. So today, I'm going to discuss situations under which we cannot do that. So transfer and reaction term are not separable. That's my purpose today, to discuss those situations. In this case, that's fine. This nice equation. But let me repeat, I'm going to discuss the cases when we cannot simply add reaction term and say, oh, this is reaction. Let me discuss another equation. Nowadays, it's very, very popular to use fractional derivatives. Very popular. For example, instead of Laplacian, I got a fractional Laplacian, and instead of a standard derivative with respect to time, I've got fractional derivative with respect to time, which is called Caputo derivative. There's many reasons why these equations are so popular nowadays. Let me give you a few examples. From mathematical point of view, we all know that behind Laplacian we have Brownian motion, right? And if we write down fractional operator, we know that behind this operator is alpha stable process. We know that. But from a physical point of view, it's a very useful equation because if we have, let's say, in population dynamics, if the particle, like animals, moves long distance with heavy tails, and second moment is divergent, of course people use this operator instead of diffusion. It's also important for physics. I'll give you just another example. If we consider, for example, Knudsen diffusion. Knudsen diffusion. It's a porous medium. And we have, let's say, the particle oxygen molecule. And we cannot explain the diffusion of particles inside the system by using Laplacian, because particles move without collisions with each other. The only collision with a wall. And sometimes that distance is distributed according to Cauchy distribution. So second moment is divergent. So if we have this nanosystem in physics, it's always useful to use this operator rather than Laplacian. So many, many examples. That's why hundreds of papers. Why we use Caputo derivative instead of standard derivative? Again, it's many physical reasons. It's because of subdiffusion. I'm sure you've heard about subdiffusion.
Yes, you have.
So if we have a particle, and we have a position of this particle, we squared it, take expectation value, and then it depends on time, not linearly, but in the power gamma, which is beta. Beta varies from 0 up to 1. So it's subdiffusion. And of course, it's a physical reason. Sometimes particle trapped and wait for a long time, such that waiting time distribution has divergent first moment. So instead of this derivative. And I've seen papers when people simply add reaction term here. From a mathematical point of view, of course, it's a legitimate model. I've got fractional PDE, then I add nonlinearity, call it nonlinear partial fractional differential equations, and I could study this equation, but the question is it a good model for reaction transfer? Why all these terms describing different phenomena are just additives? My purpose today, again, to show that in some particular cases, we cannot do that.
So what is the criteria when you say a good model?
Oh,
So what is your...
yes, good model if in some cases this equation might produce some physical result. For example, if I use here Laplacian, forget Fourier convection, and if, let's say, I put minus here, then an interaction of minus with this Caputo derivative produce negative solution. Although we assume that density is positive. Well, the reason, of course, it is mathematical consequences. But the point is, we cannot simply add nonlinearity. From probability point of view, it means that if model is non-Markovian, we must be very careful. Of course, if we have Kaputov derivative here, we all know that Kaputov derivative means a convolution of derivative with a power law function. So it's not Markovian model. Right. So that's my main message. And first, I need to remind you some ideas because I'm going to discuss this problem from physical point of view. And I'm going to use a particular language. Let's look at this equation. This is standard diffusion reaction equation. And if we specify initial condition, called space, then we know that a solution to this problem can be written in this form. In fact, this is not a solution because rho appears here and here, but this is famous Feynman-Katz formula. So from physical point of view, we could say that Feynman-Katz formula provides us a connection of microscopic Brownian motion and microscopic dynamics in terms of density. This is a standard interpretation of Feynman-Katz formula. So we have a lot of particles. They follow Brownian motion. And then on large scale, the density of particles obey this equation. And of course, the solution can be, let's say, if this is just a space, then it would be solution. Then it can be found through expectation. Now we can, of course, generalize this picture. If we say, okay, if instead of Brownian motion, we have Levy process, right? General. That in particle position described by Levy process, we could also write down macroscopic mean field equation like this, where here this generator has a semigroup defined that way. So we start the problems. It's still Markovian, no problem. Levy process Markovian, very nice, very simple, stationary, independent increment, easy. Just as illustration, compound Poisson process. If position of particle described by this formula, then we've got just a jump, and if the number of jump is a Poisson process, jumps identity distributed random variables, this is compound Poisson process, and the equation for the density looks like this. But now I call this equation mesoscopic. It's not macroscopic equation, it's mesoscopic, because from probability point of view, this is nothing else, it's just the forward equation for PDF corresponding to this process. Now I treat this forward Kolmogorov equation as equation for density. Of course, all information here is just the same, it's just different way to describe the process. Let me remind you how to derive that equation from physical point of view, not just from probability point of view. Because it's important. If I ask, what is the density of the particle at this point, x, at the time t plus h? Of course, we know that this is the density of particle at the same point, and there is no jump. And the probability no jump is 1 minus lambda h, plus particle coming from different positions here. And to take into account all this particle, we have to integrate with respect to space. We take the density at different position, x minus z. Of course, at the time t. We have to multiply by PDF for jumps, z, and integrate. And of course, it's a nice Markovian model because the behavior of the density at the time t plus h depends on the density at previous time t. So if I rearrange this balance equation, I've got this equation. So it's a very simple, nice equation. But now, if I expand in terms of Z, I can get diffusion equation. Now, if I use for jump distribution some stable distribution, I will get, of course, not diffusion equation, but fractional equation. It's a limit. So my point is that this mesoscopic equation can be reduced to two equations: standard diffusion equation and fractional diffusion equation, depending on assumptions regarding jump distribution. But of course, because it's Markovian, I can do whatever I want. I can add nonlinearity. I can take into account that jump from different position might depend on density. I can introduce nonlinearity here. I can introduce the rate of jump depending on the density. So I can create many, many nonlinear models out of this simple model. Okay, now if we slightly change the situation. Now, instead of Poisson process, I introduce counting process, renewal process, which means waiting time is not exponential anymore, but has arbitrary distribution. So, on microscopic level, this is time, this is position of particle. Let's say it starts from here, it's wave, and then jump, wave, jump, wave, jump. So it's a pretty standard picture. To describe this situation, of course, I need a joint PDF for jump and waiting time. I also introduce a jump length PDF and waiting time PDF. So I'm not going to discuss this situation. This is renewal equation, pretty standard. Later on, I'll return to this equation. So if I write down renewal equation corresponding to continuous time random walk model or semi-marked process, I will end up with this equation. So the rate of change of the density at the point x now depends on whole history, because continuous time random walk model is not Markovian. So I got a kernel. This kernel in time described, of course, memory effect, and I got explicit expression in terms of waiting time distribution. Also, of course, I've got non-locality in terms of space, as before, which is a similar phenomenon. And this function gives you the jump probability density function. Now, what about this equation? Can we add nonlinearity to this equation? That's the question. My answer is, well, we cannot do that in general. We can't simply add nonlinearity and study the problem. Why? I'll explain in a minute. Of course, if we apply parabolic scaling, this is mesoscopic equation. If we apply parabolic scaling, define this density, epsilon tends to 0, it corresponds so-called to large scale, long time limit, then for this equation we've got a simple equation. Diffusion, this is of course central limit theory. Provided that waiting time, mean waiting time is finite, and of course variance corresponding to jump distribution is finite. If not, if PDF for waiting time decrease Power law involving gamma, gamma varies from 0 to 1, and if dispersal kernel has heavy tails like this, so infinite variance, we can scale. Now we do different scaling, anomaly scale. And then we end up with this equation, macroscopic space-time fractional diffusion equation. So I just wrote explicit expression for Kaput derivative and this symmetric Riesz fractional derivative. It's many notations for Riesz derivative nowadays. This one. Again, out of mesoscopic picture, we've got different limits. Now the question is, where and at which position we can take into account nonlinearity, chemical reaction. Here, for example, I can add nonlinearity here, or I have to use mesoscopic equation. That's the question. And let me now, so this was a reminder, basic stuff. And now I'm going to take into account reaction. Of course, reaction can be taken into account in many different ways. Statistically, by using some probabilistic ideas. At the moment, I fix, and I'm going to use only the mass action law. So I just assume that reaction in general has structure reaction rate times O. That's what I'm going to use. That's my state. Again, because it's non-Markovian, involve kernel memory, we cannot add nonlinearity. That's the main result. Now I'm going to describe how to add nonlinearity.
But when you say you cannot because of some reasons.
Yes, yes.
So
what is the reason? Oh, right. Yes, exactly. Again, from a mathematical point of view, I can do whatever I want, right? I can add
not
different.
True.
Huh?
Not true.
Why?
You cannot do anything in mathematics.
Well,
You need an initial condition.
I'm talking now about equation, not boundary initial condition so far, yes. Okay, again, there's many different ways to take into account reaction, and I'm going to explain just one way. Whether it's right or not, this is a different story, but let me explain how to do it. Okay, so the main challenge is to implement nonlinear kinetic term, like this one, into non-Markovian transport process governed by continuous time Abramovich model. In mathematical literature, it's called semi-Markov process. And we assume that that's important. Chemical reaction follows mass action law. That's important. This is important. It's also convenient to represent nonlinear reaction rate as a difference between birth rate, like this, and death rate. It will be clear later on why it's important. And now let me consider two different models for reaction transfer. Model A. Of course, non-Markovian behavior of particles occur because we have non-exponential waiting time. And the reason particles just trapped at some position, they wait, and the distribution is not exponential. First, we assume the transport process and chemical reaction are independent. And we introduce the density of particle just arriving at the point x exactly at time here. And now let us implement nonlinear growth process with nonlinear markers. Let me explain how to do it. let me consider one-dimensional space. And again, I choose some point, x, and ask what is the density at the point x at the time t. The model now is not Markovian. Of course, on the right-hand side, I've got two contributions. First is the density of particle, initial, from the very beginning. They just stay here. So, what is the contribution up to time t? Of course, I have to multiply by survival probability. There is no jump up to time t. So I just multiply by survival probability. Because I've got the growth of particle, and the rate looks like this, at this point, I need to take into account the growth of particle. And I've got exponential factor, which describes the growth. Of course, it's the integral from 0 to t. I have to integrate this function. R, of course, density, the same point at different times. So this is first contribution. So what I'm doing, I'm just writing down balance equation, not evolution equation. Like the rate of change of density depends on several factors. But let me start from just simple balance equation. Of course, if I introduce the density of particle just arriving at the point x at the time t, I got another contribution. So a particle arriving at the same point at previous time, before t. Let me denote this by tau. Of course, they arrived at the time tau, which is less than t. I have to multiply by what? Survival probability again. And of course, survival probability from time t up to time, sorry, tau up to time t minus tau. And again, I've got the growth of particle. Now it's not from 0, of course, it's from tau. So I'm sure this reminds you renewal equation. But this equation is non-linear. It's not standard linear equation. So it grows. The same point, x, u. And of course, because this time is arbitrary, I have to integrate from 0 up to time t and multiply by, oh, that's all. That's a balance equation for the density. Any questions?
Why would this have a solution, this equation?
I'm not talking about
It
solutions.
doesn't explode, maybe because you have exponential.
Yes, it might
Linear.
explode, of course, yes.
So does that make sense physically?
Of course. Why not?
Yes, it explodes, goes to infinity. Finite time.
It depends on the R. But now the point is to write down right balance equation to derive an equation for the density.
But R is linear, isn't it? Is it not, generally?
What?
R could be linear in rho.
Oh yes, it might be linear. When it's linear, it just exponential grows. The same way, we can write down equation for the density. So equation for ρ, I just wrote. And the equation for the particle, so this is a rate of arrival of particle at point x at the time t. So this is also a balance equation. So I got initial distribution. Of course, I got jump PDF, which gives you redistribution of particle along space. I've got waiting time, and of course it grows. I've got two terms. So that's initial equation. Without reaction, this is a pretty standard models for continuous time runnable model.
There is reaction. R is
Without
reaction.
reaction, without.
But R is reaction.
Yes. If I is 0, if there is no reaction, it's a conservative system. This is a pretty standard equation.
If R is 0.
I is 0, no reactions. Then, of course, we have a couple of equations, linear. We can use Fourier-Laplace transform. That's pretty standard method. We can rearrange the term and derive that equation without nonlinearity. We derive exactly this equation. This is pretty standard technique, just Fourier-Laplace transform. Now, as I mentioned, we can't add that term on the right-hand side, right? Because it's possible to reduce these two equations into one equation for the density. We cannot use standard Fourier-Laplace technique because we have nonlinearity. But recently we managed to reduce these two equations to just one equation for density. This is a technical stuff. I'm not going to discuss it, but it's possible. Okay? If you differentiate, rearrange the term, we can do it. And let me show you the final equation for the density. That's equation. That's a nonlinear mass equation for the density. And now look, here we have ordinary people. So the rate of change of density depends on two terms. And now look, we have on the right-hand side nonlinearity, but this exponential factor appears inside transfer term. It's not disappeared. It's still there. So that's a main achievement of our work, because we derived nonlinear mass equation. We didn't assume any assumptions regarding jumps, waiting time, just general semi-Markov process, and then reaction. And reaction taken into account in a balance equation. Of course, if I've got that equation, I can find different limits. If I assume some waiting time distribution, I've got power law kernel, I end up with a very complicated combination of Riemann-Liouville fractional derivatives with nonlinearity. Also, if I assume that jump distribution is power law or stable distribution, I end up with a very complicated fractional derivatives. But the point is that we can't separate transport and reaction. This is just a simple mathematical result. And as I mentioned, if we reduce and we get rid of this term, we might get unphysical result, like a negative distribution, negative density. Of course, for Markov process, this kernel is just a delta function. It's easy to show. So if it's delta function, of course, this exponential factor will disappear. And we have pretty standard model. So my conclusion, of course, if we have a Markov model, that's the reason why we like Markov model. Because if Markov model, we can easily implement nonlinearity in different ways. And as long as the model is non-Markovian, then we must be very careful to implement nonlinearity.
So what you say is that when beta is 1,
Yes.
that was your order of the Caputo derivative
Yeah.
in time, then we still can add it.
That's the point, yes. So if we use like Levy process, Markovian models, fractional derivative, whatever, nice. No problem, just add. As long as we take into account memory effect, you are in trouble. And of course, people nowadays use memory effect in different areas, like another example, Fick law. The flux of particle minus d gradient of rho. But d sometimes is separated. So the flux is integral with some kernel G minus S. So we end up with a memory effect. A memory effect everywhere uses. Again, if we take into account memory effect for transport, then we must be very careful for reaction. That's my main message. But also, we've got a lot of opportunities how to take into account non-linearity. Remember, I separated reaction rate. That's birth minus death. What is the reason? Let me explain the reason. We have a movement of particle, like this. Okay? Particle, let's say, arrive at the point X, and then wait. Waiting time is given through the model. Now we have nonlinearity, production of new particle. The question is, what is the waiting time we should specify for the new particle? In Markovian case, it doesn't matter really. But in non-Markovian case, it does matter. Because, let's say, particle produced, the new particle. Should they share the same waiting time as their parents? Or I have to specify new waiting time for them? It's of course a probabilistic question, but it's also a physical question. And the equation will be different, I'll show you in a minute. I'll give you an example. If we have a cell and the propagation of virus. Viruses are small, tiny things. It's attached to the cell, then moves inside, and then proliferate. They let trap. This is point X. We just trap inside. Then we've got a production of viruses, and then what happened? The pressure due to production increases, and what happened to the cell? Just like financial bubble. And it means it's waiting time. So in this particular situation, waiting time is the same for particle produced and just attached. But we might think another situation when we have some area, the particle absorbed here, then we have production of new particle, and then it likes, we have to specify new waiting time. It's just born. H is 0. Everything depends on H. How to take into account this? This model B. The indication is as follows. Here, I have to specify only particle which dying. So it's minus, minus. Because if I got a production of new particle, remember I introduced the rate of arrival of particle at the point X at the time t. Waiting time is 0. Now I have to add reaction here, not here in this equation, but for the density of arrival. So it will be R plus rho rho. And of course, we've got a very different model. So production term appears here, and of course, death term here. But inside, only exponential corresponding to the death process. So this is another conclusion. We can add non-linearity into non-Markovian model when we assume that particle which produced given 0h. So you can see now everything depends on physical or chemical or biological situation. And equation, macroscopic equation are different. So of course the age of the particle has a transition time between two successive jumps. Again, this is pretty non-trivial equation. I solved this equation for a very particular situation I will describe in a minute. But in general, of course, I did not attempt to discuss the solution. At the moment, I just derived several equations corresponding to different models.
But the difference between this equation and the previous model A
Oh,
is that you have the negative exponential.
yes.
So that will prevent explosion in this case.
Oh, there's no here exclusion. But
Yeah,
anyway,
but in
it
the other
depends on
case you
this-
might have. Because you're using the full R.
It's like the explosion of the cell. Again, but now this is just two ways to specify new waiting time, but I could specify combinations. Also, I can take interaction. Imagine the particle which sitting at some space, point. It's either jump in the neighborhood or change phenotype. It's typical reaction. What is first? Again, in Markovian case, it doesn't matter. You have to specify two exponential distribution, they separate, but here it's a problem. So you need to clearly specify which is first, and then it create different macroscopic equation for the density. That's my main message today. So we must be very careful. Any questions regarding? Because I'm not finished yet, so I'm going to.
So it was always raised a question by Sarah in a sense about no explosion, etc. But can you actually have physical or chemical experiment which you can see that your results somehow better than or consistent with those at least consistent with those experiments?
Right. Okay. This is mathematics, and I talked about equations. Of course, if we apply this theory to two particular situations, and let me explain two situations. This is experimental fact, like the propagation of brain cancer. It's a very popular model nowadays to model cancer. We write down reaction diffusion equation, three of them, study numerically. This is all business for many, many, many years. But for us, the propagation of cancer is important because it gives us an idea how to apply probability theory. Because cancer in the brain very dangerous. And let me explain why. So we apply this theory to the propagation of cancer. Cancer, this experimental fact, can be in two states. State 1, state 2. In first state, it's proliferate. Proliferate, but it's easy to imagine the situation. There is no enough food. And if it's no enough food, proliferation stops. And cancer cells very smart. What they do? They change phenotype from 1 to 2, and in phenotype 2, the cancer cell can move. In state 1, no movement, only proliferation. In state 2, no proliferation, but movement. The particle moves very, very slowly, and the experimental fact is subdiffusion. It moves away from the point X, and then situation improved. What happened? Change phenotype again. This one, and proliferate again. If situation iterated, then of course we have another. And of course this switching happens all the time. And that switching is not simple Markovian switching. You have to take into account long waiting time because of situation, current situation, depends on other considerations. So we have a combination of slow movement, subdiffusion, and switching between two states, which are not Markovian. And again, we have to take into account this theory. We have another model describing propagation of ions in spiny dendrites. We have tubes and small spines on the top of it. And ion moves convectively or by diffusion, and sometimes trapped inside spine. And then experimental evidence, this transfer is subdifusing. And again, here we have subdiffusion and reaction come together, and also two-state system. Many physical or biological systems are relevant when we have to take into account simultaneously anomalous transfer with reaction. Okay, as usual, we wrote the paper because of experiment, published, but let me tell you, it's very difficult to communicate with biologists. That's another problem. But it's a lot of motivations to study this process. Okay, we also apply this for turbulent flow. It's pretty standard stuff about subordination. Also,
Subordination.
yes. Like the same particle position as a sum of random jump. But now the number of jump can be written in that way. In turbulent flow, we have very intensive movement, and how to model it through subordination. And if this is a Levy process, we might end up with very fine equations. This one, but this is it. And also the last comment, I got 10 minutes, about KPP equations. We also applied this theory for KPP equation. Let's look at this equation. This is a standard KPP equation. You have a diffusion and interaction with nonlinearity. It's a very famous Friedrich work who used hyperbolic scaling for KPP equation. So use this scaling, and then we'll end up with this equation. And this equation has a very simple meaning because epsilon is small, we just have a small diffusion, and because epsilon appears here, we've got a very fast reaction. Interaction of slow diffusion and fast reaction create Frank. So this is traveling wave solution in real space. And if we look at traveling wave solution from long distance, of course, instead of profile, we've got just front. This is a pretty standard theory developed by Friedrich, but it's very contradictory. In fact, let me mention why it's contradictory. Because remember, this operator, diffusion or Laplace operator, occurs as a result of parabolic scaling, right? Out of central limit theory, we have some model, apply parabolic scaling, end up with equation. And then funny things, we end up with this equation, now use hyperbolic scaling. That's not good. So my point is, this is without reaction, is attraction point. This equation, diffusion equation, is attraction point of many mesoscopic model after parabolic scale, central limit theory. But then, suddenly we forget this, put additional term and say, oh, now this is a model, let us apply hyperbolic scaling, and behind this theory actually is the large deviation theory. That's the main idea of Friedrich. And I think this is a little bit contradictory. We have to start from mesoscopic model. That's what we did. This is, we derived Hamilton-Jacobi equations corresponding to this principle of scaling. I'm not going to discuss it. It was question was asked. So we finally found rate in the subdiffusion case. So let me remind you, if you've got KPP equation, then propagation rate can be found from dimensional analysis. If you've got diffusion and reaction rate, the only way is just to do square of diffusion coefficient and reaction rate. Of course, for KPP equation, we have a minimal propagation speed, which is 2. But of course, this propagation speed is less than the classical one because of subdiffusion. And we have different expression for propagation speed for different models. Right. Right. Conclusions, well, that's main conclusion. Non-Markovian reaction transfer system is still an open problem. So we can create different models, different macroscopic equation out of microscopic modeling. And again, we must be very careful about interaction of non-linearity and non-Markovian. That's it for today.
Thank you very much. Thank you very much. Some questions or comments?
Did you say anything about scaling the equation? You know, you had those two models A and B.
Yes.
The A equation. Can you do any scaling on that and get some diffusion time?
Right. Without reaction, of course, we can do it.
Right. But with the R
With reaction, I'm very reluctant to do scaling because if I'm interested in propagation speed, I have to do hyperbolic scaling. So I don't want to scale equation for some standard fractional equation and then start again. So physically,
hyperbolic you can.
yeah, I start exactly. I write down equation, mesoscopic, very complicated, involving many terms, and then I apply hyperbolic scaling directly.
And you get some kind of equation like.
Oh yes, I've got equations, and then we can get a propagation speed.
Because I was asking this because when you scale, you really say the solution for all time. Because you have T over epsilon.
Yes.
So if epsilon goes to 0, the T goes. So how do you guarantee that the solution does not explode when you do the scaling?
That's a good question. Actually, I'm looking on the only tail, in fact.
Okay.
So, but of course, to prevent explosion, I put 1 minus rho or something.
Right, with the minus R.
Yes,
minus.
but that region is not important because after scaling, I'm interested in the tails. And tails important. What I'm saying that diffusion approximation is really bad for tails. So that's why we start from initial equations.
I have two questions because you mentioned that your model with Caputo time derivative is wrong because you may get negative solutions. But there are other types of fractional derivatives, people use plenty of them. And is it true that for every such derivative, maybe the solution could be this negativeness of your, that you have to use different derivatives?
Well, my attitude toward this problem is that all these fractional derivatives is an asymptotic limit.
Mm-hmm.
Asymptotic limit. And if initially the model is non-Markovian, we cannot simply add. We must be careful. Whatever the limit, then that's as long as not Markovian, we must be very careful. That's only the limit. Of course, we might you mean Riemann-Liouville derivative? So there's so many combinations nowadays. Yes, but again, this is asymptotic limits after rescaling.
Okay.
You consider from a master equation for density,
Yes.
and then derive some scaling. And my question is, can you consider particle description? I mean, so you first consider random walk with continuous time and derive some kind of stochastic differential equation, a system of factors, and put a delta mass for each particle. Then some kind of scaling may converge to. Can you describe?
Well, we all know that there's two different ways. One way is just to consider one particle and then consider the convergence in distribution. This is one way, pure probabilistic. But same is equivalent, right? I could write down equation for probability density function, master equation, and then after rescaling, appropriate rescaling, could see, can I get some self-similar solutions. And then, if it's appropriate limit, I've got self-similar solutions in terms of macroscopic equation rather than particular movement of particle. But I guess it is different. The question is, what is easy? Well, from physical point of view, for me, it's convenient to work with master equation rather than wise ones. And of course, if I use Fourier Laplace space, it's trivial because we all know convolution is difficult to work with in real space. In Laplace space, it's almost trivial.
From the particle system point of view, the equation should be obtained as a law of large number because it is from random one to a deterministic one. It should be a law of large number. So if you consider particle system, you may consider some kind of central limit theorem, and can you derive some master equation as a central limit?
Okay, that's no, I did not do this work. Well, this is another way to modeling. Okay, I introduce particles, then of course I introduce mean field, deviation from the mean, and specific. This is another job. A lot of work.
So, it seems there are no more questions. So, thanks again.
Well,